I'm calling for considered action, and I'm calling on specifically the U.S. Congress. The setting here is that this asteroid 2004 MN4, and I'm going to call it MN4 because it's simpler, is going to make a very close encounter, unusually close encounter with the Earth in 2029. And that close encounter sets up the possibility of a return. The problem is that in the absence of any assigned responsibility within the U.S. government, there is in fact no one to make major decisions which ought to be made. And part of my argument is that there is one decision which needs to be made within the next year or two, and I'll get to that. Okay, so in summary, as I said, I'm calling on the Congress to address those two things. Number one, identify a professional body to check the kind of work and the logic that I'm presenting here. And secondly, to in fact address the fact that there is nowhere in government today a specific assignment or any real work identified with protecting the Earth from the potential impact of near-Earth objects. Okay, what we're dealing with here is a very low probability event. That's always the case with near-Earth objects until one day when it's not. But probably none of us in this room will be around on that day. Nevertheless, even a low probability event with a high enough consequence is something to pay attention to. You and I do that every day, basically by paying $3 or $4 of auto insurance. The probability of an impact that I'm going to talk about is 1 in 10,000. That is almost precisely the probability that you or I, any day of the week, any day of our lives, will have an automobile accident, a reportable automobile accident. Our insurance, the potential loss is what, $30,000, $40,000. You multiply 1 in 10,000 times 40,000, you get $4 a day. That's about what we pay in insurance. It's smart. Okay? Right now we're driving around in the solar system uninsured. Here's the Earth, not the small dot there unfortunately, but the big round dot is the Earth. This is the error ellipse in 2029. This is a 2029 close encounter. For those of you who don't know, believe it or not, Friday the 13th of April. And we can tell you exactly where. So this is the path of the asteroid, relative motion path of the asteroid as it passes behind the Earth. I'll put some more references in there. There's the orbit of the Earth and the direction of the Sun. And you can see that it's already curving. In fact, going this close to the Earth, that asteroid, as it goes by, takes about a 28 to 30 degree right turn. Now what I'm going to do on the next slide, which is the one to really pay attention, picture yourself riding on this asteroid as it comes about to this point. Let me point out that that asteroid, that line, can be anywhere in this 3 sigma ellipse. That's the error ellipse of this particular asteroid. Just one quick word about error ellipses for near-Earth asteroids. They tend to be lines, that is extremely narrow in all dimensions except one, the one along the orbital path. Hence, this looks like a line, and it actually is damn close to it. Okay, so we now are going to go, oh, by the way, there's the geostationary orbit. So you can see that in 2029, that asteroid is going to come inside the geostationary orbit. That's how close it is. It's going to be a visual object. You don't need telescope, you don't need binoculars, just your old eyeball. The line here is the plane of the asteroid as you're riding along. And you'll notice that the plane of the asteroid does not go through the center of the Earth, it goes through the upper half in this slide. I'm going to expand that error ellipse. Here it is, expanded. There's the centroid of the error ellipse and some dimensions, which I'm not going to worry about. Okay, here's the next thing. If the asteroid passes not through the centroid, and of course, let me remind you, the error ellipse moves around as we make more and more measurements. Okay? We correct, we refine the observations, and the error ellipse in this slide would slide back and forth and gradually get smaller and smaller until it comes down to a point. The centroid may also move further and closer to the Earth, but it's been bouncing around between 5.7 and 5.58 Earth radii for the last 3 months, so it's relatively stable, and it'll probably stay pretty stable at around 5.6, 5.7 Earth radii. Now, if instead of passing at the centroid, which of course would be some kind of a miracle, it passes at this point, it's going to end up, right now it has a 323-day orbit around the Sun. It would end up with a 426-day orbit around the Sun. In other words, it gets a gravitational kick in the pants. We do this with satellites all the time, sending them out to the outer solar system. We get a kick in the pants from Venus or whoever happens to be close enough, and we can use them. Well, this NEO will get a kick in the pants, and will end up, if it goes through here, with a 426-day orbit, over a third larger than it is now, 417 days, 414, etc. That's important because these particular points, if it goes through right at the right place, it's going to come back to the Earth in 2036. In other words, 426 days and 365.25 days, if you just run it through your calculator, it says we have here a 7-6 resonance. In other words, the Earth goes around 7 more times to 2036. It takes, and it takes the asteroid only 6 times to go around. And they come back together in the same place. So each of these, if it goes through any one of these several places I've got listed here, and many others, but these are the critical ones, it will come back in 5, 6, or 7 years. But the one closest to the centroid right now of the error ellipse is the return in 2036, and that's the one I'm going to be talking about most. Okay, now let's expand that point. Okay, here it is down at the bottom. The actual resonance, where 7 years later, not only does it come back to the Earth, but the Earth and the asteroid are in exactly the same place. In other words, 5.6 Earth radii back, all over again. Okay, but if it comes a little further away, in fact, about 885 meters further out. We've changed scale dramatically here. Okay, if it's 885 meters or thereabouts from that resonance point, it hits a keyhole, and when it hits that keyhole, and I'll show the total keyhole because there is gravitational focusing. In other words, if the asteroid passes in 2029 through this keyhole, it will hit the Earth in 2036. The big question is, will it hit that keyhole, or any of the other keyholes, or will it not? All right, if you got that, we're going on. Okay, this is one of the most important slides conceptually to get. Let me explain it. This is done by Andrea Carusi in Italy. Very, very good work on his part, and it's an essential point. This vertical line is 2036, and it's the impact. In other words, if you're looking at the question of impact and possibility, what you want to do is look at an impact and then back up and say, what do I need to know when, et cetera, et cetera. But that's the way you do it. So here we have an impact in 2036, and the question is, how much delta V, how much change in the velocity of the asteroid do we have to apply to it at what date in order to cause it to miss the Earth? So we're talking deflection here. And you'll see here coming back between 2036 and, in fact, 2029, the close approach, it takes something like 1/10 of a meter per second, about 10 centimeters per second, that you would have to change the velocity of this 320 meter diameter asteroid, something close to 10 to the 11th kilograms, okay, in order to cause it to miss the Earth over here in 2036. However, because of that close approach, it drops down 5 orders of magnitude if you deflect it before 2029. Okay, that's great news. The corollary bad news, you know, it's always there, right? The corollary bad news, along with that good news that it takes very little to deflect it if you do it before 2029, is that you have to know its position very, very precisely. In fact, several orders of magnitude more precisely than you would have to know were there not a close encounter before the impact. The other conceptually easy way to understand this is in this range, you're having to change its velocity to miss the Earth. Here, you're having to change its velocity to miss a keyhole, which is only 600 meters across, instead of 2 times 6,400 kilometers across. So that's the challenge. Well, number one, it takes very little to deflect it, but before 2029, the bad news, you got to know where the hell it is. Okay, I'm going to go on to the consequences. Let's go to the other side of the equation. This is an excerpt from the current JPL table for impact risk on MN 2004 or MN4. And I'm not going to spend a lot of time on this, but what I want to do is point out in the public domain is all this information about the probability of impact of this asteroid, what date and time it's going to impact if it does, the distance above or below the center of the Earth, the width of the 3 sigma ellipse, etc., etc. All that data is in the public domain, and it's this data which I've used. However, JPL does not show you what that data means. They give you the data, but what I want to do is show you what it means. Now here is all these different parameters put together in a diagram, this obviously being the Earth. Here is that line of variations, that ellipse, okay, but it's almost a line. In fact, the width here is 51 kilometers, 3 sigma. We know today, if it hits in 2036, it's going to hit along that line. It's a very narrow ellipse, okay? It's very long. From time to time, it can get as long as all the way around the sun, okay? But it's very narrow. Okay, so, and here's the distance that you see here. So now what I'm going to show you is because you know the date and the time, and not just things like distance, you can do this. You can make that globe real, not just a blue blob. Now, don't pay attention to that. That's the only thing I could get off the web. Here's the real case for 2036. There is the path of risk for the 2036 potential impact. Again, 1 in 10,000 chance that it would hit somewhere along that line. But if it hits the Earth in 2036, it will be along that corridor, provided I've done the math right. Okay? So let's get it checked. Okay? Now, let me tell you that you can see there that the most likely consequence, although not the only one, is that it hits in the Pacific Ocean. These are the angles which it will come in at if it's on the centroid, or 45 degrees or 90 degrees, and it actually wraps around the edge of the Earth a little bit. So the question is, what happens if we get an impact out there? So I said to a friend of mine, Steve Ward, University of California, Santa Cruz, expert on modeling tsunami effects, let's drop that asteroid in the ocean there and see what happens. Here comes the event. There's the tsunami. And there are the final run-up wave heights which would occur if we had that tsunami event 1,100 kilometers off the coast there. It could be closer if it were further to the right. It could be further away and closer to Japan. But basically, those are the kind of wave heights. And let me point out that these wave heights all along the California coast are about the same as Banda Aceh in the Indian Ocean. In other words, you take the highest point anywhere in the Indian Ocean tsunami, you've got it all up and down the California coast, and even Seattle and up in areas like that, even as far away as Japan, you've got things that look like Madagascar. There have also been a number of models done on the cost of a tsunami. And if you take, I'm just going to do it right here, you go up at about 400 meters, you go across 4 million people on a global average, not that particular one, but on a global average anywhere in the oceans of the world, you're going to have about 4 million people affected. If you look at all kinds of statistics from World Bank, etc., and for a tsunami, you're basically talking about infrastructure loss, not loss of life, because you do have some warning. There will be lives lost, as there were in the Indian Ocean, but there was no warning there. You would have warning here. On a worldwide basis, the cost of infrastructure on a per-person basis, about $100,000. Therefore, the cost of that tsunami on a worldwide basis, $400 billion. If you take California's infrastructure costs, go up by a factor of 10 at least. Okay, $400 billion cost, okay, for 1 in 10,000 probability of impact. Okay, the resolution. Okay, let me just go on here to say that what we need to look at here is, obviously the resolution is to deflect the thing, but the question is, when do we have to make that decision? First of all, we want to complete the deflection by something like 2028. Okay, that means you might want to start the deflection maneuver because it takes some time, around 2026. You make a guess, 2023 to get there with the rendezvous, surveying the thing, docking with it, or if you want to do something else, impacting with it. Doesn't matter what the deflection technique is, it's going to take some time. I figure something like 2022 you're going to have to launch. To do a launch in 2022, you're probably going to have to decide to design and do this thing in about 2014. Now, you can put your own numbers in there, but somewhere around 2014, maybe 2016 if you want to take a chance, you got to make a decision. The question is, what kind of information do we have to make that decision? Okay, this is the error ellipse in 20. So what, again, a reminder, what you're looking at here is trying to look at the 2029 close pass and know whether or not it's going to go through a keyhole. All right? So what you're looking at right now is an error ellipse in 2029 that we know now is about 18,000 kilometers long. However, as time goes on, we're going to get more and more measurements, mostly optical, maybe radar in January of 2013. And gradually that error ellipse is going to get smaller. Therefore, the probability of impact, which is about 1 in 10,000 now, will go higher as the error ellipse gets smaller, so long as the error ellipse still contains the potential impact. In all likelihood, it won't. Okay? But what we're looking at is the possibility of, do we have to deflect? All right? So these are numbers out of Steve Chesley at JPL. The compression of or the shrinkage of the error ellipse will be a factor of about 4 by mid-2006, a factor of about 10 by 2012, a factor of 100 by about mid-2013. So if you've got a 18,000 kilometer, it'll come down to about 180 kilometers by 2013. 180 kilometers, and you're talking about a target that you're saying, are we going to hit it, that's 600 meters long. Okay? The maximum probability, even if it's headed for the center of the Earth, what you're going to be able to say at best is the probability of hitting the Earth is about 1 in 140. Now the question is, are you going to launch a deflection mission that costs a bunch of bucks if you've got a probability of 1 in 140? You have a lot of people who will tell you correctly that the probability it will miss is 139 out of 140. But you and I right now are saying it's going to hit. But that's the best you're going to be able to say, unless we get better information. All right, well, there's a chance of radar in January of 2013. That would reduce that by a factor of about 4 to maybe something like 45 kilometers. And then you're saying, well, maybe 1 out of 40 or something like that is the probability. Are we going to launch a deflection mission if the probability is 39 out of 40 that it's going to miss us? I don't know. And who's going to make that decision? There's nobody in government who's even looking at it, let alone setting the policy of what the accuracy has to be. Okay? So the problem then is that even using the best optical and radar tracking, the question is, even if it's headed for us, we're going to have a probability that is going to be very difficult to make a decision on. In other words, optical only, about 1 in 180, optical plus radar, about 1 in 40 probability if it's headed for the center of the Earth, if it's headed for us. And if, on the other hand, we put a transponder on the asteroid before 2012, then we'll have information which will give us a probability of impact of about 1 in 10. Now, I would suggest a 1 in 10 chance that you're going to have a $400+ billion consequence if this thing hits the Earth is probably justification adequate to decide to go ahead and launch. But without the transponder, I suggest we're not going to have the adequate information. So I'm going to bypass this so that we can get to the end. But let me just tell you, the problem here is that no one in U.S. government today is charged with the responsibility of doing this kind of an analysis, of looking at the issues of deflection, at coordinating internationally the policies. Let me tell you, as soon as you attempt a deflection, you have transformed an act of God, an asteroid hitting the Earth somewhere, to an act of humankind because you started to move that asteroid. And it doesn't just move randomly, it actually moves one way or the other along that same path until it's off the Earth. Now the question is, if you move it away from the California coast but put it over Guatemala by accident, you know, or how about moving it the other way and it lands in north of Hokkaido and you wipe out Tokyo? So there are many, many policy issues related to the fundamental decision making for somebody who's got to have in their head, my job, and I'm held responsible for it, is to think about, do we or do we not need to deflect an asteroid? And how do we do it? What are the policies, etc.? That's the issue, and today there's no agency in government. Therefore, I'm calling on the Congress of the United States to do two things. Number one, to check what I've just told you here. I've done as good as I can, but I don't have a Monte Carlo sized computer that I can start doing all kinds of fancy stuff with. I have to make approximations based on the best data I can get. But they are approximations. Okay, so number one, it's got to be checked. Number two, we've got to have somebody in government who's responsible, not just as NASA is now, for looking for these things and putting them in a database, but for actually being responsible for the decision making and all of the assorted things related to it associated with potential impact of these things on the Earth. Now, I hasten to say again, we're talking a 1 in 10,000 probability. There's not a reason in the world for anybody to lose any sleep about this, okay? Unless you're assigned the responsibility for protecting the Earth. Then you ought to be staying awake a bit. Okay, thank you very much.